go ahead and get started. Thanks everyone for joining today for this Gateway webinar. And we mean for this webinar to be interactive, so we would encourage you to interact with us through either the question and answer or the chat box. Today's webinar is going to be on kind of adjusting for space and thinking about space and environment and how we think about that with exposures. And we're very happy that Kaylee Keller, who's an associate professor from the Department of Statistics at Colorado State University, and one of the people working with us on the Gateway to help us think through these issues, is going to be presented. So I'll turn it over to Kaylee, and I believe she's going to take questions at the end.
Thanks, Tristan, and thank you all for being here for this webinar. So as Tristan said, I'm going to be talking about how we might adjust for space and analyses with environmental exposures. And I'll try to give some examples along the way about how this ties into some of the questions that can be asked with the Gateway data. To provide just a brief overview of an outline for my talk today in this webinar, first I want to briefly mention the objectives, what I hope you can gain out of being part of this webinar here today. And then I will talk about confounding in general, and then how it plays into spatial confounding. So what happens when we add space to that? And then look at how we can adjust for confounding using spatial fixed effects and spatial splines and some example results from those. So I'll say a little bit throughout about some of the mathematical details in part, some of the coding details in part, but my big picture focus today for us is going to be on the concepts and why we might do these types of adjustment and the kinds of questions we have to address to implement it in practice. And so my objectives for us today is that for participating in this webinar, that you'd be able to describe the concept of spatial confounding and describe different approaches that are available to you as an analyst or as a researcher for ways you could adjust for space and regression analyses. And even if you're not someone maybe who's hands-on with the data, I hope these are helpful things to think about in terms of questions you might ask your research team or colleagues or others you work with. And lastly, I want us to be able to interpret results from an epidemiological analysis that includes spatial splines. So to get started with just confounding in general. So confounding is the distortion of a relationship between two variables due to the influence of a third. There's various different ways it can be defined technically, but I like to think about confounding in terms of this diagram here at the bottom, where we're thinking of, we're interested in this relationship between an exposure here and a health outcome. So we want to estimate this arrow and understand, quantify what's this relationship here. And a confounder is a variable that's causally related to the outcome of interest and to the exposure. So if we're thinking about these arrows representing causality, at least in a general sense, this confounder causes something about the health outcome, and this confounder causes something about the exposure. And if we have a setup like this, then if we ignore whatever this confounding variable might be, that's going to be problematic in our analyses. We might end up with an answer that's different from the one that we would like to get. To give some examples, as opposed to just broad concepts, one way you might think about this is if we want to estimate the relationship between exercise and cardiovascular health, we probably want to start thinking about the role of age, because age is causally related to differences in cardiovascular health, and age is related to differences in exercise. Now, it doesn't mean that age perfectly predicts your health or perfectly predicts the amount of exercise you do, but it's going to be related. And so that's what's represented in this top diagram here. Or in the bottom diagram, if we're interested in relationships, say, between indoor biomass burning and birth weight. So this comes up in analyses of projects I've been part of looking at things like cook stove replacement programs and connections with pregnancy outcomes. If we want to estimate this connection here, we want to make sure that we're thinking about the role of secondhand smoke, because that can relate to other exposures which might impact birth weight, as well as it's going to potentially be correlated with biomass burning as well. So those are just two of the many different kinds of examples where confounding might arise and ways in settings where we want to start thinking about doing something about that. Now, what do we typically do about confounding? Generally, the way we approach this from an analytical perspective is to estimate what are sometimes called conditional associations. But basically, we're saying we want to think about what is the comparison among people or among households or among whatever our study unit is that have the same value of the confounder. So what is the average difference in an outcome variable for a 1 unit difference in an exposure variable among observations with the same confounder variable? That's really kind of the generic form of the question we might ask. So in the context of those two examples I just gave, we could say, okay, among people of the same age, is there an association between exercise and cardiovascular health? Or among households with the same number of people who smoke, is indoor biomass burning associated with infant birth weight? So we're conditioning on saying people of the same age or households with the same number of people who smoke. That's how we can adjust for this confounding in our analyses to try to get the answer that we want. If you prefer a more mathematical take, this is really what happens when we fit regression models, where if we're thinking about modeling a health outcome, which is usually on the left-hand side in these types of equations, we model it as a function of an exposure and a confounder and an error term. And so by having this confounder on the right-hand side, in the math of the model, if we end up with a beta here that is the coefficient of x, that is the difference in the average value of y for a 1 unit difference in x among observations with the same value of the confounder, the c. Now, if you don't like math, this is just the conceptual framework that we're working in here. This is just the math that goes along with that. But the idea is if we add it to the model, then we're comparing basically among units or among people, again, among households that have that same value of whatever that confounder variable might be. So how does this relate to issues in the gateway, and where does space come in? So as many of you probably know, right, over the last couple of years, we've been working to add environmental exposome data to the gateway to bring in that data along with all of the other harmonized data that's going to be there. And so there's information on fine particulate matter air pollution, nitrogen dioxide air pollution, ozone air pollution, data on nighttime light and light exposure during nighttime hours, access to green space and blue space. So that's like access to like things like parks or the distance you are from water. So these are all variables that we're interested in incorporating into the gateway. And there's kind of the broad question that we want to know is, these would allow us to estimate how do these exposures relate to cognitive aging? Now, that's a question that's going to take a lot of work, and it's not one that I'm prepared to talk about the answers to today, but that's part of the motivation for starting to talk about space, since all of these different factors here, all these 6 different exposures that I've listed, all vary across space. They're not necessarily solely a function of space, but they will vary across different cities, across different countries, and across different regions. And so if we want to analyze spatial exposures, basically we fit the same kind of model. If I'm thinking about a regression framework, again, that's a framework that lets me estimate relationships between some exposure x and some exposure y. The biggest thing on this slide is just I've added a new letter here. I've added in this S. So now we're thinking about things varying by space. So your air pollution exposure is going to depend on part on where you live and where you spend your time. So the big picture here is that everything is starting to depend on space as well as just individual level characteristics. And now the problem comes up, well, what if there are additional confounding factors we don't measure? So we might have this, I've listed here, this is Z, confoundant and adjustment variables. These are factors that maybe we measure and want to account for. So this could often things be like age, perhaps a measure of socioeconomic status, or like the size of a family unit. It might be something about your individual level health risk factors. These are things we measure and maybe want to account for in our analyses. But what if there are things that we haven't measured that are also playing a role? And so that's where we're going to start to run into this problem of confounding from space. So say there are other things we haven't measured. That's what's represented here, just this f of s term. F just means a general function of space. It could be one factor we've missed. It could be a lot of different factors we missed. But these are things that we either haven't measured, so they're unmeasured, or incompletely measured. So in the kinds of problems that come up in environmental epidemiology, this might be something like urbanicity. Usually we do want to adjust for some sort of urban-rural categorization or continuum, but maybe we've not measured that completely. So maybe we've measured it incompletely and not fully in the way that's relevant to the health outcome that we're studying. Maybe we have information on cultural practices that varies widely across large regions, depending on general kind of regional trends. Or maybe we have measures of socioeconomic status or deprivation that, again, maybe we've got one measure of it, but not all of the measures of it. So there is spatial structure that we're missing in what we have. And so we have this unmeasured term here. We can also have confounding by space that's due to like geophysical characteristics. So this can be like climate or elevation, which can be related to health outcomes as well as related to environmental exposures. So sometimes it's characteristics of social characteristics or characteristics of the ways individuals live, and sometimes it might be confounding by location due to geophysical characteristics. And so if we ignore this term, we can have bias in our health estimate. So we want to include it in there, but the problem is we can't, right? So I've set this up as saying, well, this is all the things we haven't measured. So how can we include it if we don't measure it? And that's really the crux of the problem of spatial confounding, is that we have confounding by space or location. It's the inability to distinguish the effect of a spatially varying exposure, which here is denoted by this X term, on from residual spatial variation in the outcome, which is this F term here. And so if we have this stuff we haven't measured, but it does vary across space, that's going to be problematic. And it's going to lead to bias. Because if I go back for a moment to this list of environmental exposures, anything that varies across space is going to have some amount of correlation with these. Maybe not a high correlation, but things that vary across space are naturally correlated across space. And so we will have potentially some bias and incorrect answers we might come upon if we don't account for space correctly. If you prefer pictures, another way to think about it is, say, if we're interested in the relationship between the exposure and our outcome. So in this setup, I've just got a square grid. So this is kind of like a fake data, but the color represents different levels here. And so we're interested in estimating the relationship between this exposure on the left and an outcome on the right. But these are both actually also impacted by some unmeasured factor. And so we want to account for this unmeasured structure, this unmeasured spatial structure in our analyses. Otherwise, we might have bias in our results. And so the way we can go about doing this is really just a natural extension of the confounding adjustment approaches that I mentioned a few moments ago that we use in our regular analyses, but where we want to just add something to, say, a regression model. I mean, in this case, we want to add known spatial terms. So we have our environmental exposure. We have those other measured factors for each individual in our study, but we want to add space to the model. And this will, in general, hopefully account for spatial confounding and give us a better answer. The details of how we go about doing this is really what I'm going to talk about for the rest of our time here today, because that's where the challenge comes in. There's different ways to think about different spatial terms we could use: county or state, climate region, spatial splines. Then we also have to ask this question of how many terms to include. There's some data-driven approaches. We might use expert knowledge. And so now I'm going to talk about both of these questions in turn. First, talking about different ways we can account for what spatial terms we might use, and then talk a little bit about how things we need to consider when we're looking at the number of terms that we should include. So the first approach we might go is want to just adjust for spatial fixed effects. And so this is accounting for location using basically indicator variables of the region or the spatial unit that an individual is in. So this might be something like state, county, province, district. It might be something like an indicator for climate region. But we're just adding a term to a model here. From my background, I think of these as indicator variables. You might have heard them referred to as like dummy variables in analysis or fixed effects, depending on your background and what language you're familiar with here. But the idea is we're going to say we're going to add a term that says, what state do you live in, for example? And then so we can compare differences in exposure and the outcome among people who live in the same state. And that will account for some of the spatial variation. And so it allows for separate outcome intercepts by region, which will help reduce some of our confounding. And it's really equivalent to estimating associations when exposures are scaled within a region. And I'll have a picture about that in just a moment. I do, though, just want to point out, this isn't the same as stratifying by region. When you stratify an analysis, you're basically taking your cohort and splitting it up into a bunch of different smaller groups. We're not doing that here. We're just adding a region term to our model to account for it, to adjust for it, but we're not interacting with everything. So we're not stratifying. So in pictures, in terms of we're thinking about spatial fixed effects, for some of our examples today, I just want to use an example from the United States. This is California and Nevada are the states here. So if you're not familiar with the geography of the United States, this is the US, or excuse me, this is the Pacific Ocean here on the left. This is kind of on the west coast, southwest coast of the United States. So we've got California, Nevada. Here about the middle edge of California is where San Francisco is. Los Angeles is down here at the bottom. So this is just to give us an example of something to work with and look at here. So if I want to adjust for state in the US, that's just what this is colored by here on the left map. Or if I wanted to, for example, adjust by county, that's what's colored by on the right map. So you have all these different varying spatial units that vary across space. In this case, this is just the different counties that we have. So how does this relate to exposure? So in this plot, I'm showing on the far left, this is a plot of PM2.5 across that same region. So across California and Nevada. So PM2.5 is particulate matter air pollution. It's one of the, like if you're thinking about what it looks like when you see wildfire smoke. That's a little bit bigger particles, but it's the same kind of idea in terms of particulate air pollution that we might see. And in this map, these yellow values here represent larger values, and the darker colors represent lower values. And so we've got variation across this region. If you know some things, if you're familiar with the geography of this area, you know there's like a large valley here, then there's kind of mountains in the middle. So there's geophysical explanations for why we see some of these patterns. But if I want to think about looking at this as an exposure and analysis, and I want to center it by state, I get something that looks like this plot in the middle. So what's changed here is, in this case, I've centered each exposure within Nevada, and centered the exposure within California. So you can start to see this like sharp edge here that happens between the states. So this is one of the downsides to adjusting for space using these like geopolitical units, is you end up with like these sharp edges that end up impacting your results. If I center by county instead, so the counties are smaller in this region, but you still see some of these sharp effects. You can see that kind of down here on the this area where there's like a dark line and then other colors there. So we end up with a little bit of strange edge effects, and which might lead us to say, okay, maybe this isn't the best way to adjust for space. However, it really is a very convenient way to adjust for space, since a lot of time our data is already aggregated by these kinds of geopolitical units. And so we might want to do this just because of it's kind of straightforward and simple and pretty easy to interpret, because we can say, okay, we're comparing people who live within the same county, who live within the same state, or whatever it might be. And this is going to really treat the state, county, region like any other confounding variable. So just in our analysis description, we could say, well, adjusting for county, the estimated association is ... or whatever it might be. So that's one way we can approach this problem. But this issue of edge effects here is potentially a little bit problematic. So can we do something perhaps better, or at least a little different, to give us another option for adjusting for space? And that's going to bring us to splines. Splines are a really useful mathematical tool, but they sometimes can be a little bit difficult to understand if you're not if you've not worked with a lot of mathy objects. So I'm going to try to talk about it in terms of pictures and hopefully something that is a little bit easier to understand. Basically, splines are like building blocks for complex functions. So it's a series of simple things that when you add it together in the right way, you can get something more complex. So visually here, I've got 4 pretty simple surfaces that I've got. And if I combine them in the right way here, then I can end up with this more complex surface. If you prefer to not think about surfaces, another way to think about this is just in the numbers we use all the time. Like the number 172. You're really combining 100, 10, and 1 in different ratios to come up with this more complex number. It's the same idea. So I've got 1 of these 100s here, and then 7 of the 10s and 2 of the 1s, and that gives me 172. Splines are the same idea. We're just doing it with spatial functions instead of just with numbers. And for adjusting for space in epidemiological analyses, what we typically do is thin plate regression splines. So they're a computationally efficient spatial basis. That just means that basically that they're easy to calculate. They have some nice mathematical properties. There's good software for calculating them, and they work well when doing adjustment across space. So this plots shown here show basically the different, the first 10 splines. So each of these looks like kind of a weird, pretty simple spatial function. This one's kind of varying left to right. This one's varying top to bottom. This one's varying in a circular fashion. So they're all individually pretty simple. But together, they give us a set of building blocks which we can estimate more complex surfaces. So how does this play out, like, again, in our example of California and Nevada here? So what I've plotted here are some of the different splines we might calculate across this region. Now, the actual numbers aren't important, so I've not shown a scale or anything, but you can just see some color variation here, light to dark across these regions. And we start with these first few are kind of varying much more smoothly. There's not, going from the top left to the bottom right, things vary pretty slowly as you go left to right. Whereas this one on the bottom right, there's a lot more spatial variation. So we've got different amounts of flexibility, and the more splines we add, the finer scale variation we can model. So basically, it gives us a lot more flexibility, the more pieces you have to work with. Like the more Legos you're building with, the more complex of a structure you can build. In terms of this, how it plays out with exposure data, if I go back to our PM2.5 example here on the left, I could actually break this down, this exposure on the left, into a part that we could explain by splines and a part we could not explain by splines. So this is just using the first 5 splines. I can take these original concentrations I have on the left, and what I can explain by 5 splines is the surface here in the middle. Now, these two scales are the same. And so this one here, it just kind of looks like you've got this general left to right trend. It looks pretty smooth. There's not nearly as much detail here in this middle plot as there is on the left plot. And that's because with 5 splines, with 5 Legos, with 5 building blocks, we actually can't capture very strong spatial variation. And so what we haven't measured is what's left over here on the right. So again, we're basically taking the left side and splitting it into the middle and the right. And these two pieces together, if you added them back together, would get you back to where you started. So that's if I'm using 5. If I'm using 25, I can start to do a little bit better. You can see that if I'm using 25 splines, then I can actually start to capture some of this trend here. So some of the patterns we see with this big valley in California start showing up in this plot. And so we're doing a little bit better. If we give us more things to work with, again, we can build more complicated spatial surfaces. If I go up to 100, I can do even better. You start to see more variation here. So the takeaway from this part is just that splines give us a way to model spatial variation. And the more you add, the more flexible things can get. So again, if I just go walk back through these, starting with 5, if you just focus on the middle plot going through here, we've got very little spatial variation. If we do 25, we can do a lot more. And if we go to 100, we can do even more. So the more you add, the more flexible you get. So there's a couple ways we might bring this into an analysis. One of the ways is we could do this is really similar to the pictures I was just showing. We could basically say, let's take our exposure and split it into a part we can explain by splines, that's this part here, and a part we can't explain by splines. So we're just taking that exposure and splitting it into X hat and an R. If you are familiar with mathematical terminology, the R comes from residuals. If you're not, you can just think about this as the explained part and the unexplained part here. And what we do is we just take that and put that into our original model. And this term, this coefficient for the residual part, won't be confounded by spatial variation that's explained by TPRS. So if we go back to the picture for the moment, what we've done is we've taken this exposure and are splitting it into a part that's explained by splines and a part that's not explained by splines. So what we're doing is getting rid of confounding variation that happens on this scale of this middle plot, and we're left with just this kind of smaller scale variation that we're still using to estimate our health effects or whatever else we might be interested in. So we've kind of gotten rid of problems that happen on a scale like this. So maybe you can already kind of tell this is an approach that works well to capture long range trends, kind of big picture trends in an area, since this is going to be several hundred miles across or several hundred kilometers across in this region here. So that's one approach. But the approach that I would actually end up recommending, which is where we'll focus on for the rest of the time here today, is to add splines to our model. So again, instead of going into this kind of splitting our exposure up into 2 pieces, let's take our model and just add thin plate regression splines to it. And so this is, again, following that same approach of let's add a confounder variable to our model. We estimate a conditional association, and we can get rid of bias or at least reduce bias in that way. This type of approach is really a direct extension of something that's been used for several decades in environmental epidemiology for time series studies. And you may have seen this come up in your own work and study or projects you've been part of or seen, where if you want to account for like seasonality, for example, you might add a smooth function of time so that it can vary over time. If you want to adjust for year or month, you might add temporal terms like that. This is doing the same thing, it's just doing it in space. So in this case, we're adding spatial splines here to this analysis in a way that basically we will account for confounding up to however many splines we include in the model. This does require being able to calculate these splines at all the locations, but thankfully that's actually pretty easily computationally. So that's not a problem for us in practice. So very briefly, kind of how can we actually implement this kind of model? I've got a few slides here with some R code just to show how it can be done. Hopefully, my goal here is to convey that it doesn't take too much additional work if you're already familiar with R. Again, if you have specific questions about how to implement this in practice, I'd be happy to take questions about that at the end or follow up offline one-on-one if that would be helpful for you or your colleagues in your project. So there's a package in R called MGCV that has a function called GAM and then also a function just called S. And the S there stands for smooth. This is the function, it was put together by Simon Wood, really almost 2 decades ago now, that can create splines for us. So there's a function here where we can input our coordinates and get the splines out. So I'm going to go to the next slide, which will just look at this R code here in a little bit more detail. And so if we've got our data set where we've got some exposure X, an outcome Y, a measured confounder Z, and then we've got coordinates. So this could be like latitude and longitude that we might be working with. We can fit a GAN model here where we have Y tilde X plus Z plus then this S function is what's adding the splines for us. So if you're familiar with R, you might recognize this as the usual way that formulas are input into it for a regression equation. It's usually the left-hand side is the outcome. The tilde is kind of functions like the equals. And then on the right-hand side, you just add together everything that you want to adjust for on your model. So here I say, okay, I want to do 5 splines that are based off of these 2 coordinates here in my analysis. And I fit this model and I can pull out, for example, in this case, the coefficient for X, which would be my estimated health effect. So this is a really powerful approach. There's a lot of different things you can do through this smoothing function within MGCV, but I think this is almost too powerful for a lot of cases. There's a lot of ways you can accidentally kind of mess yourself up and trip yourself up using the MGCV package. So instead, what I've put together with some of my colleagues and people I've worked with over the last several years, a package spconf, which will allow you to pre-create the splines, and then you can kind of just treat them like a regular variable. So if I go back for a moment to this other approach, we've got kind of the variables we're used to having, and then I have to do something special here with space. I think it's a lot easier for us to think about this problem if we don't have to do something special with space. And so this package is a way to create spatial splines in R that then you can add splines to any model you have. So I've highlighted this in yellow because I really think this is the power and flexibility. If you make the splines in this way, then you can just add them in like regular variables to any other kind of modeling object you have, whether that's like a proportional hazards regression model for survival data. If you're part of a team analyzing survey data and have complex survey weights, you can throw it into there. Or if you're just doing regular linear regression, that works as well. So there's a function that's called compute TPRS here, and this is in the spconf package, where you just give it the coordinates and tell it how many splines you want, and it will create output like what's shown here in the bottom. So I've cut this off, but basically this is going to be a data frame or like a matrix that's giving us a bunch of values. Each row here represents a different location I have. Depending on your data, that might be different individuals, or it might be different grid points or anything, or different county regions. And it's got 5 columns for the 5 splines. Now, these numbers of themselves don't really mean anything. I'm not trying to interpret what this 1.0966 means. I just want to think about, okay, I've got 5 splines in my model, so let's add it to a regression model. So I can end up, if I just add it into my data frame, then I can fit a model here. This is just using a standard multiple linear regression model. Y is a function of X plus Z plus TPRS1, TPRS2, TPRS3, TPRS4, TPRS5. So I'm just putting it in there like a regular variable, and that lets me estimate, again, my health effect estimate, in this case, adjusted for 5 splines. So the nice thing about this approach is that you can create these splines ahead of time and then just fit and add them into your regression model. Now, if you're working with a larger project team, this might be helpful because you could actually, you could have a team member create the splines and then everyone use those variables in analysis, as opposed to having to create it on the fly all the time. So this is the approach that I would recommend if you want to include splines in your analysis, is to follow that spconf approach, where you create the TPRS ahead of time, and then you can just add it to the regression model like normal. So in general, though, this approach, which I had labeled as approach 2 on the slides, we're just adding splines to the health model. It treats space like any other confounder. And generally what we would say is we're adjusting for a residual spatial variation, say with 10 thin-plate regression splines. The estimated association is, and you can explain it like normal. So it's just another way to add a flexible term to our model that's going to account for confounding by space. If you feel kind of confident and savvy in R and spatial statistics, the MGCV function and package can give you a lot more flexibility to do other things. But I think for most users, just sticking with the spconf approach is the way to go. So we've got this way to adjust for space. I said, okay, we can add splines, and I said a little bit about how adding more splines accounts for more complexity. But I think there's still some important questions that are not answered yet. 2 of them are, well, what does it mean to adjust for this many splines? Like, how does that relate to spatial distance? And then how do we pick how many to adjust for? So this plot here is a preview of some results I'll show a little bit more later on. But basically, as you move left to right here, things are changing. And so this is saying fitting models going from 3 splines in the model all the way up to 50 splines in the model. This is my estimate of a health association in this from a specific cohort, and it starts to change. So depending on how many splines you add, whether you add 5, whether you add 10, whether you add 20, that can change the results you get. And so that can be potentially problematic and something we want to avoid. So first of all, how do we just interpret this in terms of spatial distance? So working with Maddie Rainey, who is a graduate student who works with me at Colorado State University, we've put together a tool for calculating what we call an effective bandwidth. But basically, it's a way to say, I want to take the number of splines. So that's in this plot, that's what's on the horizontal axis down here at the bottom. So how many splines in the model, and relate it to a physical spatial distance. So this is labeled effective bandwidth here, but this 10, 100, 1,000, you could really think about that as 10 kilometers, 100 kilometers, 1,000 kilometers. Now on here, we've plotted these lines that are going down. What this is basically trying to represent is that saying the more splines we add, the smaller spatial scale variation we can model. So if I was going to say, for example, I'm working on data from Ireland, and I include 10 splines in my model, that means I'm basically smoothing over ranges that are about 100 kilometers in size. But if I would go up to 100 splines in my model, then I'm working more about 15 kilometers. So the more splines you add, the smaller spatial scale of variation you can model. And this gives you a way to basically compare across countries and regions. So for something like the gateway, we think this is really helpful because, what does adjusting for space mean in the United States? Perhaps something that's very different from adjusting for space in India or adjusting for space in England. Like all of those have they're different sizes, there's different shapes, there's different things going on. And so this gives us a way to kind of compare across countries. How many splines we include impact the results we might see. We've also put together an interactive Shiny app, which allows you to visualize this for different areas. So this is just showing an example where we've got like a 10-kilometer grid across England. And so taking these data points as input, we could calculate again, what is the distance in terms of like kilometers that corresponds to a different number of splines here across the horizontal axis. And so we can see how this plays out in England, or we could see how it plays out, for example, in India, in this case, using a 50-kilometer grid. So in addition to plots of figures, there's also results tables here. So if in this case, from this data input, adjusting for 10 splines means smoothing at about the scale of 650 kilometers. So again, this is designed to give you as the analyst or the researcher a tool to kind of understand, okay, how many splines I put in map to distance, and how does that vary across different regions? Because that's going to be different, again, in like England compared to India, for example. There's also an option here to upload your own coordinates. And so if you have data from your cohort or your study and you want to see what it looks like, or if you want to create your own grid across maybe a subset of one of these countries, for example, you can upload that into this app and then calculate these values on your specific data set. So that link here at the top is the link to that Shiny app, it's g2aging.shinyapps.io/spconfshiny. So this is built on top of an R framework, and it's through the R Shiny framework. But it calculates the effective bandwidth for splines in different regions, and there's preloaded data in there for England, for India, for Ireland, and Northern Ireland, and the United States. It's also possible to upload your own coordinates. Now, you only want to do that if you, don't have sensitive data. There's also, if you want to prefer, you can download the spconf package. That's what this Shiny app is built on top of, and you can calculate all these metrics on your own machine, on your own computer, if you prefer and need to do that. So again, working with Maddie, we've got a technical manuscript that's going to explain both some of a citation for the algorithm and how we calculate these values, as well as more on how to interpret them and how to compare them. That's forthcoming and hopefully will be out by the end of this year. So that answers one of our 2 questions that we had left. It was this kind of answers this question of, well, what does it mean to adjust with k-splines? We can use this effective bandwidth to at least put a spatial distance on things. But we also now have this question of, well, how do we pick what distance to use? And this is also potentially challenging. So what I want to show here, this is a snapshot of a figure from a paper that was doing kind of a technical comparison of different things. But what I want to draw your attention to here is on this left panel here, this black line. So what's going on here is as you move left to right, that's basically adding more and more splines to a model. And you can see that once we've added a certain number, then things just flatten out. That's ideally where we would like to be. We want to say, okay, once we've added enough splines, we've gotten rid of bias. We're recovering the true estimate, the true association, and we can go forth and really be confident in our analyses. So this is one scenario where that does happen. But in this plot, again, just want to draw your attention to these black solid curves in each of these 6 panels that vary left to right. As you're going left to right, you're doing more adjustment. And this is kind of in this top one here. Oh, wait, we do more adjustment. Do we do more adjustment? We do more adjustment. We finally hit the truth, which is represented by those blue dotted lines there on the bottom. So this is okay. We have to add more splines to get the right answer than we might otherwise, but that's doable. But this bottom left is really kind of the challenging scenario. In this case, adding more and more and more actually moves this black curve away from the blue dotted line. So this is a scenario where adding more variables, adding more adjustment for space actually makes things worse and worse for us. And so that's really one of the dangers we have is we can't just say, oh, well, add enough to see where things stabilize. We don't necessarily know that things will stabilize. And so that's going to be a challenge we have when adjusting for space analyses. There are also a lot of data-driven approaches. So this is just kind of a snapshot, really wanting to just highlight that there are different technical approaches that have been developed. All of these approaches use different statistical techniques for trying to understand, okay, I want maybe 10 splines or I want 20 splines, penalization. There's a lot of different flexible options here. And you can see just from these references, this has really kind of grown in popularity and flexibility over the last 5 years or so. So there's a lot of options here. But I bring this up just to say there's options out there, but in my experience, a lot of them don't work that well. And so in terms of like, I can't say that this one approach will give you the best answer every time. So these data-driven approaches can vary in effectiveness. And so right now, again, with some of my colleagues and students that I work with, we're working on comparison manuscripts of these to give more specific guidance of how you might use one method in a particular setting versus another. So look for that in the coming months. But in general, I think I would say for a lot of epidemiological studies, we don't necessarily want to use one of these data-driven approaches. We want to use the kind of a priori expert-informed selection here. Because the biggest challenge we have is just that adding more doesn't necessarily mean we'll end up with less bias. So the kinds of things we have to consider in this kind of analysis is, well, how much non-spatial variation is there? And is the exposure measured or is it modeled? So if this will come up in different in the gateway, thinking about some of the different exposures. So our PM2.5 measurements come from a really complex global model that allows us to make predictions of air pollution at different locations around the globe. But it also means that there's some smoothness to it because we're not actually measuring, we're not sticking a monitor out on a 1 kilometer grid. So that would take like billions of monitors to cover the whole world. Instead, we've got measurements in different locations and make predictions. And so that means there's less spatial variation in the exposure than in some of the other settings. Whereas, for example, the nighttime light, that's satellite data. We're actually measuring that. And so it's going to have more non-spatial variation. And so that is something that comes into play where if you have more non-spatial variation, you might do more spatial adjustment. Another question you might ask is, well, what is the hypothesized confounding factor? What are you worried about missing? Is it variation across a large scale, or is it variation like within a city? That can help tell you how many splines you might want to put in your model. So just to move towards the end here, showing some examples, I've got examples from 3 different cohort studies where we actually adjusted for splines, different number of splines, and want to show you the different numbers of results we might get. So in the NIHS sister study, where we're looking at exposure to ambient air pollution, ambient particulate matter, and its effect on blood pressure, this was a cohort of almost 50,000 women, adult women, where we had their exact GPS location. We knew their latitude and longitude of their residence. And then so we could look at it, including everything from 3 splines up to 500 splines. And you can see here that as we did more and more adjustment, we moved towards basically a result that just included 0. So this was a case where if we did too much adjustment, we actually ended up eliminating any health effect estimate that we saw. And this, so what ended up happening based off of consensus of the research team for the primary analysis, they chose 10 degrees of freedom, which is going to be adjusting on a scale of around 1,000 kilometers. So this is like about a regional adjustment. So that was the decision that was made by that research team. But hopefully you can see from this plot that there's, where you choose to be along here can make a big difference. So generally you want to make this choice a priori before you've seen the results to protect yourself from type 1 errors. Just to give another example, this is using data from eczema and air pollution, looking at no adjustment to increasing amounts of adjustment as you move left to right in this figure. So this was among children in the United States who are part of the Medicaid cohort, looking at exposures to particulate matter air pollution, nitrogen dioxide, and ozone air pollution, where we're interested in the relationship between air pollution exposure and incident eczema in the first year of life. So this is newborn infants. And here we had area level location information. So zip code tabulation area is kind of like a neighborhood census unit here in the United States. So we had data on that scale. And you can see here, what I just want to point out here is that for these two pollutants, the red circles at the top for NO2 and the green triangles for ozone here, you can see they kind of track. As we do more adjustment, the estimates get a little bit larger and then stay about the same. Whereas for PM2.5, it actually goes in the other direction. So doing spatial adjustment can affect different environmental exposures in different ways. And so in this case, we're just seeing different trends from different pollutants that has to do with the different spatial scales of the variables and their spatial variation. But you don't always end up with the same effect. So this is another reason where you want to ideally choose the amount of adjustment. So choose where you want to be here on the horizontal axis ahead of time. A final example here was looking again in the Medicaid cohort, but this was looking at asthma-related hospital admissions as it relates to particulate matter air pollution. So there's two kinds of particulate matter air pollution here, PM2.5 and PM coarse. PM coarse are just larger particles that you might again see from like wildfire smoke or something. So here I just want to point out that again, as you go left to right, these lines start to diverge. So doing adjustment is affecting different pollutants in different ways. So this was a scenario where we decided ahead of time to use 15 splines, but then after we were done, we went back and looked at, well, what would have happened with other amounts? And so you can see, again, these changing trends. Additional examples, if you're interested in other papers out there. So some of what I've shown so far has been a little bit more on the mathematical, statistical, technical side. These are two papers which are on the epidemiology clinical side, looking at air pollution exposure and blood pressure in the sister studies. So this is the primary reference for the example I gave just a moment ago with the sister study, and then also with some of our colleagues who are also a part of the Gateway, who are looking at the HRS cohort in the United States, a comparison of particular PM sources and incident dementia. This was another analysis where they adjusted for space using splines. So in general, hopefully I've convinced you that adjusting for space can be critical in environmental epidemiology, and certainly adjusting for it can change your results. There's methods to adjust for space, either using fixed effects for county, region, etc., which can be useful if you already have predefined units. But spatial splines via the MTZV package and the spconf package give us a tool to adjust for space in a more flexible, smoothly varying way. Data-driven evaluation is really complex. So my primary recommendation is that you consider plausible mechanisms and make an a priori selection about how many splines to use in a particular setting, and really want to use contextual knowledge you have about factors that might be important and kind of the scale you have of your data, that can be used to inform the choices that you have and make for your particular data set. Links here for the Shiny app as well as that spconf R package. I can come back to these references if you have any technical questions, but want to acknowledge my collaborators on this. Maddie Rainey, who works with me here at Colorado State University. And some of this early work was a collaborative effort between me and one of my earlier mentors, Adam Spiro at the University of Washington. And also I'm working on this with the Global to Gateway Aging Exposo team now. And we'll be adding more of this as part of the environmental exposome, and want to thank the NIH for funding. And now I'd be happy to take any questions you have. Thank you for your attention and time.
Thanks, Kaylee. That was great. And just for all the participants, so you can ask questions either through question and answer, that box, or through the chat box. And also, just so you know, we'll put the recording of this webinar on the Gateway documentation page, as well as the slides. So if you wanted to refer to them later, those should be available to you.
I'll just add, I know that depending on your background, this might be a lot of new material thinking about space in this way. So we'll be working with the Gateway team to incorporate more information and kind of additional tutorials, which might break down additional kind of pieces of the big picture that was talked about here today. So also look for more information and different types of information forthcoming as we continue to expand the Gateway exposome.
All right, well, maybe there are not any questions. Thank you so much, Kayla. That was a super interesting presentation.
Looks like we have a question just came through.
Oh, perfect.
Okay, great. So reading from the Q&A question, are there issues to be aware of when combining splines with Krieg values of environmental exposure? And what questions can we ask content experts to guide decisions about the amount of smoothing through Krieging and the number of splines in a model? So these are great questions. So I want to go back just a moment to one of the slides here. So I really think this question ties into these factors to consider. So Krieg values of environmental exposure. Krieging is one method of doing spatial prediction. So if you're not familiar with it, it's basically a way to spatially smooth across points. And so if you've got these predictions from a Krieging model or a model that's closely related to Krieging, basically if you do too much adjustment, you will just essentially wipe out the effect. So actually that's what's happening here. In this analysis, we were using an ambient PM2.5 exposure, which was predicted from a Krieging model across the United States. And really, once you get up to about 100 splines, we've essentially wiped out all the spatial variation from the Krieging model. So one of the things, I guess, to be aware of, if you have details of the Krieging model and could ask, like, what is the spatial range parameter in that Krieging model, you don't want to adjust for too many splines such that you're just essentially wiping out the full range. So that would be one way you could approach this question. I also think in terms of asking content experts questions in terms of what are you worried about? I think one of the things we think about in the United States is there's differences in composition of air pollution, for example, across different regions, and so that's operating on a larger scale, on the order of like hundreds of kilometers. So oftentimes when I've been part of analyses, that's variation in composition as well as variation in kind of like state level social and medical policies is the kind of variation we're interested in worrying about. And so those are cases where we have adjusted for at a larger number of splines. In other settings, if you're worried about kind of finer scale variation, you might add more splines, or just kind of think through what are the variables you wish you'd measured, and then think about the scale they operate on. So those are some of the questions that come up in discussion. I will say it's often an ongoing dialogue at least for the teams I'm part of, between the economists, the clinicians, the statisticians, the whole team, to try to understand what is it we're most worried about. And we'll sometimes also pre-specify, say, we are choosing this number, and we're pre-specifying also to look at additional sensitivity analyses as a way to say, kind of, if we were wrong and it was something else, what might be the difference? And so that is one of the ways we kind of go about trying to make sure that our results are robust and resilient to this amount of adjustment. So hopefully that answers the question. If not, please feel free to follow up with another one there. And then also, what would make up the process of deciding the number of splines to use a priori? So it's kind of related to these questions that we would ask is, what are we worried about? So what's the hypothesized confounding factor? What do we think is the spatial scale of variation in our exposure? So again, if it was like a Krieging output, you might actually have that in terms of a parameter, like a spatial range parameter from the covariance function, or you might be able to look at your data set and estimate what that range is. So that's actually something for the Gateway that I'm working on, trying to estimate, from all of these different global models, what is the spatial scale of variation in the exposure? And so we want to make sure we want to stay under that amount of variation when we add splines to a model. So it's really thinking about these different questions, and then trying it out and see what happens. I will say it's taken for the teams that I'm part of, we've built up familiarity with how these splines operate across the United States. I'm less familiar with how they operate across other spatial regions. And so that's also one of the reasons why we developed that tool, that Shiny App tool, to help try to make these comparisons. Because I think it is can be helpful if you have different experience or different exposures that you are familiar with in your context. You could look at them. Another thing you could do, just to add to this, is you could say, oh, I want to take my environmental exposure and just model it as splines. So early on, when I had that picture of like the California, Nevada, splitting it up into like the 5 splines or the 25 splines, 100 splines, that's another way to try to understand like what is the scale of variation in your exposure. And that kind of gives you an upper limit of the number of splines you'd want to include in a model. And so do something less than that. So there's a lot of fluidity here, but it also can be very contextually driven to make that decision. I guess I will add one other thing. I think sometimes that is also done in projects is we'll adjust for like say like a region or a district or province or something like that. And then also in a separate analysis adjust for splines and look at the consistency there across those results and the robustness there as a way to evaluate, are we capturing the same thing? Are we capturing different things? And then look into what might be potential mechanisms if we see a difference there.
All right. Well, barring any for last minute questions, I just want to, on behalf of the Gateway team, just thank Kaylee for this presentation. I think it's very interesting, and I appreciate you talking about it more widely with us. And we look forward to the coming resources you're helping us develop.
Thanks for having me and for everyone's time and attention during the webinar this morning, and look forward to continuing to work with the Gateway team.
Thank you.